Bismillahirrahmanirrahim. In this video we are going to prove Gauss divergence theorem using Green theorem. So, we will use the concept of the Green theorem to prove Gauss divergence theorem. We proved in previous videos that the Green theorem says on a closed curve integral dx m dx plus n dy is equal to double integral over the given region partial n partial x minus partial m partial y dr, where dr is equal to dx and dy. So, we proved this theorem, and now we are going to prove using this Green theorem to prove Gauss divergence theorem. So, in fact, we have this is in the plane, this theorem apply in the plane xy plane. So, we have to extend it to space, three-dimensional space. Okay, so let us start at m dx plus n dy is in fact mi nx nj dot dxi dyj, and we write it a, this one is vector a and this is dr. Okay, we can write it a dr ds and ds. We know that this value is unit tangent. So, this is a vector a dot unit tangent ds. So, in fact, we have a closed region in the xy plane. At certain point there is a tangent, unit tangent, and the ds is a increment of this path ds, and a is a vector field in which we take this closed path. So, a is the you can say vector potential or vector field. Okay. Now, we see that there should be a normal over here, unit normal n. So, T and n are lies on the screen, lies on the xy plane, let us say, and we have a third vector k which is perpendicular to n and t. So, using this concept that this is t, this is normal n, and here is k, k, it is k. So, this angle is 90, this is also 90. Okay, so that is unit tangent. So, the unit tangent can be written is k cross n. The unit tangent is equal to k cross n. So, putting this in this, let us say, one equation, then one equation implies that m dx plus n dy is equal to a dot, this t is now k cross n, all of them are vector, and ds. Using the scalar triple product, scalar, this is a k in a scalar triple product. So, we can interchange the cross and dot, a cross k dot n ds. So, m dot dx plus n dy, m dx plus n dy is equal to a cross k dot n ds, where all of them we know ds is the arc length element, n is the unit normal to the curve, k is the unit vector along the z axis, and a is the vector field, vector potential. Okay, we name this a cross k is b. But what is this a cross k? We see a is m I n j, that is a, cross k. So, this value is b, but we see that I cross k is minus j. So, minus m j, and j cross k is I. So, that is n I. So, this is b, this is vector b. So, this is in fact vector perpendicular to the plane lies the plane containing a and k. Okay, so, we can write now m dx plus n dy is equal to b dot n ds. Okay. Let us find the divergence of b as well. Divergence of b is equal to partial partial x I partial partial y j apply on b, which is n I minus m j. Okay. So, here is the divergence of b, that is partial n partial x minus partial m partial y. So, that is the divergence of B. So, now we have these two values m dx and dy is equal to b dot n ds. Also, we have partial m partial n partial x minus partial m partial y. This is the divergence of B. And we know by Green theorem that on a closed curve m dx plus n dy is equal to double integral over the region partial m partial n partial x minus partial m partial y dx dy. Now, putting the values, this is equation 2, 3 and equation 4. So, put equation 2, 3 and 4, we have integral over the closed curve. This m dx n dy is b dot n ds is equal to double integral over the region and this value is written as the divergence of B from 3 and dx dy we write it as dr. So, we can write it as dr increment of the region divergence of B dr. So, this is the Green theorem in vectorial form. So, I am writing it again, Green theorem in vectorial form. This is B dot n ds equal to double integral over the region divergence of B dr. This is the Green theorem. So, what physically it says, we have a closed region in the xy plane and ds is the increment of this region, this is ds, and dr is dx and dy. So, is an areal increment. So, ds is ds is arc length increment and dr. So, I will write ds is arc length increment. And dr is area increment, this areal increment. Okay, now this is divergence theorem in plane, but if we want to define it is in space x y z, then this closed curve will be a closed surface like the sphere and ellipsoid. So, closed surface, in that case it will be a closed surface. So, for that closed surface, this ds is a areal increment. This will become areal increment. We have a small pitch on the surface ds. Okay. And this dr will goes to dv, which will be equal to dx, dy and dz. That will be volume increment. Volume increments. Little cube. So, volume increment this is. So, the divergence theorem then take the form. Okay. This n will be a normal vector, to the surface n. So, this equation 5 takes the form for 3-dimensional space. We can write it double integral over the surface of the closed region b dot n ds. Now, this ds is areal increment, surface areal increment. This is surface increment is equal to triple integral over the region divergence of b dv. This is Gauss divergence theorem. So, on the left side we have a surface integral and on the right side we have volume integral. So, in a 3-dimensional space we have a closed surface, and S is the surface area, and V is the volume. So, ds is the surface increment and dv is the volume increment. So, the divergence of b from the closed surface is on the right side integrated over the whole volume is equal to surface integral b in the direction of n normal. So, on the left side we have surface integral and on the right side we have volume integral, and they are equal by Gauss law, and we follow the step of the Green theorem. Green theorem is in fact the divergence theorem, but it is in the plane xy plane. Gauss divergence theorem is for the 3-dimensional space and it is for volume and closed surface. Okay, thank you. If it is helpful, like, comments and subscribe. Thank you.